Hello, and thank you for joining me on this journey. Tonight, we will slowly drift into a world of volcanoes and deep earth forces, where immense heat, pressure, and shifting rock shape the planet from far below the surface. Imagine vast magma chambers moving through the mantle, feeding volcanic systems that rise through tectonic boundaries, mid-ocean ridges, and hotspot chains scattered across oceans and continents. From towering stratovolcanoes to hidden underwater fissures and even colossal supervolcano calderas lying beneath familiar landscapes, each formation tells a story written over billions of years. In the distance, you can sense the Pacific Ring of Fire, where the edges of plates constantly reshape land and sea. These forces influence climate, build new islands, enrich soils, and quietly guide the evolution of life itself. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. Volcanoes originate where Earth's internal heat finds pathways toward the surface, often along tectonic plate boundaries or hotspots where mantle plumes rise. These structures are not isolated features, but expressions of a dynamic planetary system constantly recycling crust. Beneath the surface, molten rock called magma accumulates in chambers, pressurized by surrounding rock and gases until conditions allow it to ascend, shaping landscapes through eruption or slow intrusion over time. As magma rises, it evolves chemically, separating minerals and gases that influence eruption style. Basaltic magma, common at mid-ocean ridges, flows more easily due to lower silica content, while andesitic and rhyolitic magmas trap gases more effectively, increasing explosive potential. This compositional variation explains why some volcanoes produce gentle lava flows, while others generate catastrophic explosions capable of reshaping entire regions. Tectonic plates act as the primary framework for volcanic distribution across Earth. At subduction zones, one plate descends beneath another, melting under pressure and generating magma that feeds volcanic arcs, such as those surrounding the Pacific Ocean. These arcs, collectively known as the Ring of Fire, contain the majority of Earth's active volcanoes, linking deep ocean trenches with towering volcanic mountain ranges. Mid-ocean ridges represent another major volcanic system, forming where tectonic plates diverge and magma rises to create new oceanic crust. These underwater volcanic chains extend for tens of thousands of kilometers across the seafloor, continuously reshaping the planet's lithosphere. Although hidden beneath vast ocean depths, they produce more volcanic material annually than all land-based volcanoes combined. Supervolcanoes differ from typical volcanoes in scale rather than form, defined by their ability to produce eruptions exceeding 1,000 cubic kilometers of material. These systems, such as Yellowstone in North America, develop massive magma chambers capable of collapsing and forming calderas hundreds of kilometers wide. Their eruptions are rare, but capable of global climatic disruption through ash and aerosol injection into the atmosphere. Underwater volcanoes, or submarine volcanoes, often remain unnoticed despite their abundance. When eruptions occur at depth, immense water pressure alters eruption dynamics, causing lava to cool rapidly into pillow-shaped formations. These structures accumulate over time, sometimes growing into islands if volcanic activity persists long enough to break the ocean's surface, as seen in volcanic archipelagos across the Pacific and Atlantic Oceans. Volcanic gases play a crucial role in eruption behavior and environmental impact. Water vapor is the most abundant, followed by carbon dioxide and sulfur compounds, which can influence climate when released in large quantities. Sulfur dioxide, in particular, can form reflective aerosols in the stratosphere, temporarily cooling global temperatures after major eruptions by reflecting incoming solar radiation back into space. Volcanic lightning occasionally appears during explosive eruptions, generated by electrical charges created through ash particle collisions. As ash plumes rise rapidly through the atmosphere, friction between particles separates charges, producing intense electrical discharges. These lightning events illuminate eruption columns and provide scientists with additional insight into plume dynamics and particle behavior within eruptive systems. Lava viscosity determines how far volcanic material can travel before solidifying. Low viscosity lava can flow long distances, forming broad shield volcanoes like those in Hawaii, while high viscosity lava tends to pile up near vents, forming steep stratovolcanoes. This physical property is controlled primarily by temperature and silica content, linking chemical composition directly to volcanic morphology and landscape evolution. Volcanic activity has played a foundational role in Earth's long-term habitability. Early volcanic outgassing contributed to the formation of the atmosphere and oceans, releasing water vapor, carbon dioxide, and nitrogen over geological time. Without these processes, Earth's surface environment would lack the chemical balance necessary to support complex life, making volcanism an essential component of planetary development. Rising beneath oceanic hotspots, mantle plumes transport unusually hot material from deep within Earth's interior toward the crust. These columns of buoyant rock can remain stationary for millions of years, while tectonic plates drift above them, forming volcanic island chains like Hawaii. Each island records a different stage of activity, with older landmasses gradually eroding and sinking back beneath the ocean surface over geological time. Basaltic lava dominating hotspot regions displays low viscosity due to reduced silica content, allowing it to travel long distances before solidifying. This mobility produces broad shield formations with gentle slopes rather than steep cones. As successive eruptions accumulate, massive edifices rise from the seafloor, eventually breaching the ocean's surface. The Hawaiian archipelago represents one of the clearest examples of this long-lived volcanic construction driven by mantle plumes. Yellowstone represents a supervolcano system fueled by a large magma reservoir beneath the North American continent. Geological surveys indicate repeated large-scale eruptions over the past 2 million years, each reshaping the surrounding landscape into vast caldera structures. Beneath the surface, heat from partially molten rock drives geysers and hydrothermal features, revealing the dynamic interaction between crustal stress and deep magma accumulation. Subduction zones generate some of the most explosive volcanic activity on Earth due to the introduction of water-rich oceanic crust into the mantle. As descending plates melt, volatile compounds are released into rising magma, increasing pressure and gas content. This combination leads to highly explosive eruptions capable of producing towering ash columns and widespread pyroclastic flows that rapidly reshape surrounding terrain. Plinian eruptions represent one of the most powerful eruption styles, characterized by sustained columns of ash and gas reaching extreme altitudes. Named after the Roman observer Pliny the Younger, who documented Mount Vesuvius, these eruptions eject fragmented magma at high velocity. The resulting ash disperses across vast regions, influencing air quality, climate patterns, and even aviation routes due to its atmospheric persistence. Pyroclastic flows move with extreme speed along volcanic slopes, consisting of superheated gas, ash, and rock fragments. These dense currents hug the ground, driven by gravity and thermal energy, reaching areas far from the eruption source. Temperatures within these flows are high enough to instantly incinerate organic material, making them among the most dangerous volcanic phenomena associated with explosive activity. Lahars form when volcanic debris mixes with water from rainfall, melting snow or crater lakes, creating fast-moving mudflows. These mixtures can travel along river valleys for great distances, carrying boulders, ash, and sediment. Even after an eruption ends, lahar events may continue for years, reshaping valleys and floodplains while depositing thick layers of volcanic material across previously stable landscapes. Seafloor spreading along mid-ocean ridges continuously generates new crust as magma rises and solidifies beneath the ocean. This mechanism gradually expands ocean basins while recycling older crust at subduction zones. Basaltic eruptions along these ridges often form pillow-shaped structures due to rapid cooling in seawater, preserving distinct rounded forms that accumulate into extensive underwater mountain chains spanning the globe. Volcanic monitoring systems rely on seismographs, gas sensors, and satellite imaging to detect early signs of unrest beneath active regions. Subtle ground deformation often precedes eruptions as magma moves through subsurface chambers. By tracking these signals, scientists can identify patterns of increased activity, improving hazard assessment for populated regions located near active volcanic zones and reducing potential risk exposure. Stratospheric aerosols produced by large eruptions can influence global climate by reflecting incoming solar radiation. Sulfur dioxide released into the upper atmosphere transforms into fine particles that remain suspended for extended periods. These particles reduce surface temperatures temporarily, demonstrating how volcanic activity can extend its influence far beyond local regions and interact with planetary-scale atmospheric systems. Rising through fractured basaltic crust, lava tubes develop as the outer surface of a flowing stream solidifies, while molten material continues moving beneath it. Once the interior drains away, long hollow conduits remain, sometimes extending for kilometers underground. These formations preserve evidence of past high-volume lava transport and often include collapse features that open skylights into the hidden subterranean architecture of ancient eruptions. Shattering under extreme thermal stress, obsidian forms when silica-rich molten rock cools so rapidly that crystals cannot organize into a structured lattice. The result is a volcanic glass with a sharp, reflective surface and conchoidal fracture patterns. Archaeological findings show it was widely used for cutting tools due to its precision edges, while modern geoscience uses it to study rapid cooling dynamics in eruptive environments. Harnessing Earth's internal heat, Iceland demonstrates how geothermal energy emerges where tectonic divergence and volcanic systems intersect. Subsurface magma heats groundwater, producing reservoirs of steam that can be converted into electricity and direct heating systems. This interaction powers much of the nation's infrastructure, while surface features such as geysers and hot springs reveal continuous heat transfer between molten rock and circulating water. Within active craters, lava lakes represent rare surface expressions of persistent molten reservoirs, where convection keeps liquid rock circulating beneath a partially solidified crust. One volcano in Hawaii has maintained such a feature for extended periods, with its surface level rising and falling in response to gas pressure and magma supply changes. These lakes provide direct windows into shallow magma dynamics rarely observable elsewhere. Categorization of volcanic forms reveals distinct structural patterns shaped by eruption style and magma chemistry. Shield edifices are broad and gently sloped. Stratovolcanoes are steep and layered through alternating explosive and effusive deposits, while cinder cones form rapidly from fragmented ejecta around a single vent. Each volcano type reflects long-term interactions between eruption frequency, viscosity, and subsurface pressure conditions. Encircled by steep walls formed from collapsed magma chambers, caldera lakes occupy some of the most dramatic volcanic depressions on Earth. These water-filled basins can reach significant depths and often display unusual chemical compositions influenced by surrounding rock. Variations in mineral content may produce striking colors or acidity levels, reflecting ongoing interaction between groundwater systems and the remnants of ancient eruptive collapse. Across fertile regions shaped by ash deposition, volcanic soils known as andisols support highly productive agriculture due to their mineral richness and moisture retention capacity. Weathered lava and ash release essential nutrients such as potassium and phosphorus over time, enhancing plant growth. Regions surrounding active volcanic zones frequently sustain dense agricultural communities because of this naturally enriched substrate formed through long-term eruptive cycles. Beneath the thick cloud cover of Venus, radar mapping has revealed extensive volcanic plains and large shield-like structures spread across its surface. These formations suggest widespread resurfacing events throughout its geological history. Although direct observation is limited by atmospheric density, thermal data indicates that internal heat may still drive molten activity beneath the crust, making Venus one of the most volcanically modified planets in the solar system. Towering above Martian terrain, Olympus Mons represents the largest known volcano in the solar system. Its immense base spans hundreds of kilometers, formed through repeated lava flows accumulating over immense timescales. The absence of plate tectonics on Mars allowed this volcano to grow unchecked above a stationary hotspot, producing gently sloping flanks that rise far higher than any comparable structure on Earth. Releasing superheated gases through fissures in Earth's crust, fumaroles often form in active volcanic regions where subsurface heat interacts with groundwater systems. These vents emit compounds such as sulfur dioxide and hydrogen sulfide, leaving distinctive chemical traces used in monitoring subsurface activity. Nearby seismic disturbances frequently accompany these emissions, as shifting magma bodies fracture surrounding rock and generate volcanic earthquakes deep below the surface. Tracing deep time through geologic layers, volcanic ash deposits serve as precise chronological markers that help scientists reconstruct Earth's history. Even thin ash beds can be correlated across continents due to unique mineral signatures. These tephra layers allow researchers to align sedimentary records, track ancient eruptions, and understand how explosive events influenced climate shifts and ecosystems across vast geographic distances. Expanding across Iceland's Rift Valley, fissure eruptions release lava through elongated cracks rather than a central vent. These linear openings can stretch for kilometers, producing curtains of molten rock that flood surrounding plains. Over time, repeated fissure activity builds extensive basaltic plateaus. The interaction between tectonic separation and mantle upwelling makes Iceland one of the most active volcanic regions on the planet. Compressed beneath kilometers of rock, magma chambers evolve through cycles of replenishment and cooling, creating layered reservoirs of partially molten material. Differences in density cause chemical differentiation, separating lighter silica-rich components from heavier minerals. These chambers act as staging zones for eruptions, where pressure buildup determines whether material will remain stored underground or ascend rapidly toward the surface during volcanic unrest. Illuminating the night sky with intermittent bursts of glowing fragments, Strombolian eruptions are characterized by rhythmic gas-driven explosions. These events eject incandescent lava bombs and ash in relatively short bursts, often building small cones around active vents. Named after an island volcano in the Mediterranean, this style represents moderate eruptive energy compared to more violent explosive systems driven by high-pressure gas accumulation. Embedded within subduction zones, volcanic arcs form curved chains of active centers that mirror the geometry of descending tectonic plates. These arcs appear both on continental margins and island chains, producing a wide range of magma compositions. The chemical evolution of ascending magma reflects interactions with surrounding crust, contributing to diversity in eruption styles and long-term landscape formation. Dramatic collapses of volcanic edifices can occur when magma chambers are rapidly emptied during major eruptions. The unsupported rock above subsides, forming large depressions known as calderas. These features may later fill with water or continued volcanic activity, creating complex landscapes that record both destructive and constructive geological phases within a single system shaped by internal heat and structural instability. Eruptive columns rising from explosive events can reach the upper layers of the atmosphere, where winds disperse ash over continental scales. Fine particles carried within these columns can remain suspended for extended periods, influencing atmospheric clarity and aviation safety. The vertical structure of these plumes provides valuable information about eruption energy, gas content, and the interaction between rising magma and surrounding air. Transforming oceanic crust at convergent boundaries, subduction zones recycle lithospheric material back into the mantle. As hydrated minerals descend, they release water that lowers melting points in surrounding rock, generating magma. This mechanism drives many explosive volcanic systems around the Pacific Basin and explains why volcanic activity is concentrated in regions where tectonic plates converge and interact dynamically over geological time. Detecting subtle ground deformation above magma reservoirs, satellite radar interferometry has become a critical tool in modern volcanology. By comparing repeated orbital scans, scientists can identify swelling or subsidence that indicates subsurface magma movement. These measurements provide early insight into potential eruptive activity, improving understanding of how pressure changes propagate through volcanic systems beneath populated regions. Subglacial eruptions occur when magma interacts with ice sheets or glaciers, producing rapid melting and explosive fragmentation due to extreme thermal contrast. Meltwater can accumulate and later release in sudden floods known as jökull loups, reshaping valleys downstream. Iceland frequently experiences this type of activity, where volcanic heat and glacial environments intersect to create highly dynamic and rapidly changing landscapes shaped by both fire and ice. Deep beneath volcanic arcs, fluids released from subducting slabs reduce the melting point of surrounding mantle rock, generating magma with distinctive geochemical signatures. These fluids originate from altered oceanic crust, carrying water and minerals downward. As pressure and temperature increase, they trigger partial melting that feeds long-lived magma systems responsible for many explosive eruptions along continental margins. Stabilizing themselves over stationary hotspots, volcanic chains record plate motion across millions of years. As tectonic plates drift, older islands gradually move away from the heat source, becoming inactive and eroding over time. This sequential formation creates linear island chains that serve as geological timestamps, allowing scientists to reconstruct plate velocity and direction with remarkable precision. Magnified under laboratory conditions, volcanic ash reveals angular fragments of glass, crystals, and rock broken apart during explosive eruptions. Grain size distribution provides insight into eruption intensity and fragmentation depth. Finer particles can travel great distances through atmospheric circulation, while coarser fragments settle near the source, forming distinct stratigraphic layers that preserve eruption sequences within sedimentary records. Interacting with seawater at hydrothermal vents, volcanic activity on the ocean floor supports unique ecosystems powered not by sunlight, but by chemical energy. These environments host organisms that rely on chemosynthesis, deriving energy from hydrogen sulfide and other compounds emitted through fissures. Such systems demonstrate how volcanic heat can sustain biological communities in extreme and lightless conditions. Accumulating over centuries, lava domes form when highly viscous magma slowly extrudes from a vent and piles up near its source. These steep-sided structures often grow unstable as internal pressure builds, sometimes leading to explosive collapse. Their formation reflects magma rich in silica, which resists flow and traps gases, contributing to episodic eruptive behavior rather than continuous effusion. Revealing internal structure through seismic tomography, scientists map variations in rock density beneath active volcanic regions. These images highlight zones of partial melt, magma storage, and solidified conduits. By analyzing how seismic waves travel through Earth, researchers can identify hidden reservoirs and better understand how magma migrates before reaching the surface during eruptive events. Extending across the Pacific Basin, the Ring of Fire contains a majority of the planet's active volcanic systems. This horseshoe-shaped region is defined by intense tectonic interaction where multiple plates converge and subduct. Frequent earthquakes and eruptions result from continuous crustal recycling, making it one of the most geologically dynamic areas on Earth, with persistent volcanic activity. Breaking through solidified crust layers, Dyke intrusions occur when magma forces its way upward through fractures in surrounding rock. These vertical sheets of molten material can cool and solidify underground, forming resistant structures that later become exposed through erosion. Dikes record the pathways of ancient magma movement and help reconstruct the internal plumbing of volcanic systems. Oscillating between dormant and active phases, many volcanic systems exhibit long periods of inactivity punctuated by sudden reactivation. These cycles depend on magma supply, chamber pressure, and crustal stress conditions. Dormancy does not indicate extinction, as subsurface magma may remain present and capable of renewed ascent when conditions allow, sometimes after centuries or even millennia of apparent stability. Reaching extraordinary heights on distant planetary bodies, volcanic structures such as Olympus Mons on Mars demonstrate how low gravity and lack of tectonic plate movement allow continuous buildup of lava flows. Without lateral crustal motion to shift hotspots, eruptions accumulate in one location, producing immense shield formations that dwarf terrestrial volcanic systems in both scale and volume. Recording subtle tremors beneath active regions, seismology provides critical insight into magma movement before eruptions occur. Small earthquakes often increase as molten rock fractures surrounding crustal material during ascent. By analyzing wave patterns, scientists can distinguish between tectonic stress and volcanic activity, improving early warning systems and revealing how pressure accumulates within subsurface magma reservoirs over time. Shifting across ocean basins, hotspot tracks preserve a chronological record of plate motion as volcanic islands form sequentially above a stationary heat source. Each island represents a different stage of volcanic evolution, from active eruption to erosion and subsidence. This pattern allows geologists to estimate plate velocity and reconstruct the long-term movement of Earth's lithospheric plates. Expelled during explosive eruptions, volcanic ash can alter aviation routes due to its abrasive effect on jet engines. Composed of fine glass shards and mineral fragments, ash clouds pose significant hazards to aircraft, even when visually difficult to detect. Monitoring systems track these plumes across atmospheric layers to ensure safe navigation and reduce risks associated with high-altitude flight through contaminated airspace. Forming under extreme pressure deep within Earth's mantle, magma generation depends on temperature gradients, mineral composition, and volatile content. Partial melting occurs when specific minerals liquefy while surrounding rock remains solid. This selective melting produces chemically distinct magma types, which influence eruption style, viscosity, and gas retention, ultimately shaping the morphology and behavior of volcanic systems at the surface. Spreading outward from mid-ocean ridges, newly formed oceanic crust records, magnetic reversals preserved in basaltic rock. As lava cools, iron minerals align with Earth's magnetic field, locking in directional information. These magnetic stripes provide evidence for seafloor spreading and plate tectonics, revealing how volcanic activity continuously renews oceanic crust while driving long-term geological change across ocean basins. Surrounding many active volcanic regions, geothermal gradients increase sharply due to proximity to shallow magma bodies. Heat transfer through fractured rock warms groundwater, producing hot springs and geysers. These features indicate subsurface thermal energy and provide accessible evidence of volcanic systems operating beneath the surface, even when no eruption is visible at the surface environment. Eruptions beneath glacial ice generate rapid melting and fragmentation due to extreme thermal contrast between magma and frozen water. Resulting meltwater can accumulate in subglacial reservoirs before sudden release, producing powerful floods that reshape downstream landscapes. These interactions between ice and volcanic heat are particularly common in high-latitude regions, where ice sheets overlay active volcanic zones. Incorporating chemical signatures from surrounding crust, ascending magma evolves as it interacts with different rock types during its journey upward. Assimilation of material changes its composition, affecting gas content and viscosity. These transformations influence eruption style, determining whether magma erupts explosively or effusively, and contribute to the diversity observed across different volcanic regions worldwide. Detecting ground inflation through satellite radar imaging, scientists observe subtle swelling above magma chambers as molten rock accumulates underground. These changes in surface elevation often precede eruptive activity. Continuous monitoring allows researchers to track deformation patterns and identify potential unrest in volcanic systems before surface eruptions occur, improving hazard assessment in populated areas near active zones. Constructing layered edifices over repeated eruptive cycles, stratovolcanic systems build steep profiles through alternating deposits of lava, ash, and debris. Each eruption contributes to the complex internal structure, recording a history of both explosive and effusive activity. These volcanoes often dominate surrounding landscapes due to their height and dramatic slopes shaped by long-term accumulation of diverse volcanic materials. Buried beneath continental crust, ancient volcanic provinces, known as large igneous provinces, represent some of the most extensive eruptions in Earth's history. These events released enormous volumes of basalt over relatively short geological periods, reshaping entire landscapes. Their formation is linked to mantle plume activity and may have influenced past climate changes and mass extinction events through atmospheric gas release. Cooling rapidly upon contact with air or water, volcanic glass forms when molten rock solidifies without crystallization. Obsidian is the most common natural example, displaying sharp fracture patterns and high silica content. Its formation requires extremely rapid cooling conditions, often occurring at lava margins or underwater eruptions, where heat loss prevents mineral structures from organizing into crystalline forms. Expanding outward in circular patterns, shield volcanic systems develop from repeated low-viscosity lava flows that travel great distances before solidifying. These structures are typically broad and gently sloped, built over long periods of consistent effusive activity. Their internal composition reflects stacked layers of basaltic rock, each representing individual eruptive episodes that collectively construct massive volcanic edifices over geological timescales. Revealing thermal anomalies from orbit, infrared satellite sensors detect heat signatures associated with magma near Earth's surface. These observations allow scientists to monitor remote volcanic regions and identify areas of increased activity. Variations in surface temperature patterns often indicate subsurface movement of molten rock, providing valuable data for assessing potential eruption risk in otherwise inaccessible environments. Circulating through hydrothermal systems, seawater interacts with hot volcanic rock beneath the ocean floor, becoming enriched with dissolved minerals. This chemically altered water emerges at hydrothermal vents, supporting unique ecosystems dependent on chemical energy rather than sunlight. These environments demonstrate how volcanic heat influences ocean chemistry and sustains biological communities in deep sea conditions. Reshaping landscapes through repeated collapse and eruption, caldera-forming events represent some of the most significant volcanic transformations. When large magma chambers empty rapidly, the overlying crust loses support and sinks, creating vast depressions. These features may later host lakes or renewed volcanic activity, preserving evidence of catastrophic eruptive history within their layered geological structures. Generating seismic waves as magma forces its way through fractures, volcanic tremor signals continuous movement within subsurface systems. Unlike short earthquakes, these vibrations can persist for extended periods, indicating sustained magma flow. Monitoring such signals helps scientists understand internal dynamics and track changes in pressure and fluid movement beneath active regions. Transforming planetary surfaces beyond Earth, volcanic activity has shaped multiple bodies in the solar system. On Venus, extensive basaltic plains suggest widespread resurfacing events driven by internal heat. On Jupiter's moon, Io, intense tidal forces generate continuous volcanic eruptions, making it one of the most geologically active objects known, with constantly changing surface features dominated by molten sulfur compounds. Accumulating ash layers over time, sedimentary records preserve evidence of past explosive eruptions. Each deposit contains mineralogical signatures that allow researchers to identify source regions and eruption magnitude. These layers serve as chronological markers in geological studies, linking volcanic events to climate variations and environmental changes across different periods of Earth's history. Descending through Earth's crust, subducting oceanic plates, transport water and sediments into the mantle, where they influence magma formation. Released fluids lower melting temperatures, generating magma that feeds volcanic arcs. This recycling of crustal material connects surface processes with deep Earth dynamics, sustaining long-term volcanic activity along convergent plate boundaries across the planet. Stretching across Iceland's mid-ocean ridge system, fissure eruptions often release lava through elongated fractures rather than centralized vents. These eruptions can extend for kilometers, producing extensive basaltic flows that reshape large portions of terrain. The interaction between divergent tectonic plates and rising mantle material creates persistent volcanic activity, making Iceland a key natural laboratory for studying crustal formation. Encasing gas bubbles within rapidly cooling lava, vesicular rocks form when volatile compounds escape from molten material during solidification. These trapped cavities create lightweight textures and provide insight into gas content within erupting magma. Pumice is a common example, capable of floating on water due to its high porosity and low density resulting from explosive volcanic fragmentation. Monitoring deformation patterns with high-resolution GPS networks, scientists track subtle ground movements above magma reservoirs. These changes often indicate pressure buildup beneath the surface as molten rock accumulates. Even millimeter-scale shifts can signal evolving conditions within a volcanic system, offering critical information for forecasting potential eruptive activity and understanding subsurface magma dynamics in real time. Accumulating thermal energy within shallow crustal environments, geothermal fields associated with volcanic regions provide natural sources of heat and steam. These systems are commonly harnessed for electricity generation and heating. The interaction between groundwater and residual magma creates persistent energy output, demonstrating how volcanic systems continue to influence human infrastructure long after eruptive phases have ceased. Revealing layered histories through stratigraphy, volcanic deposits preserve sequences of eruptive events over time. Each layer reflects a distinct eruption, allowing scientists to reconstruct the frequency, magnitude, and composition of past activity. These geological records help establish timelines for volcanic systems and provide context for understanding long-term changes in Earth's surface and atmospheric conditions. Expanding beneath the ocean floor, pillow lava formations develop when molten rock erupts underwater and cools rapidly upon contact with seawater. This process creates rounded, interconnected structures that stack over time. These formations are common at mid-ocean ridges and provide direct evidence of continuous volcanic activity occurring in deep marine environments across global oceanic systems. Sustaining long-term heat sources within planetary interiors, mantle convection drives the movement of material responsible for volcanic activity. Hot rock rises toward the surface, while cooler material sinks deeper, creating circulation patterns that transport energy throughout Earth's interior. This dynamic system underlies the formation of magma and influences the distribution of volcanic regions across the planet. Ejecting fragmented material during explosive eruptions, pyroclastic deposits accumulate in thick layers surrounding active centers. These materials include ash, pumice, and rock fragments that settle rapidly after being expelled. The resulting deposits can reshape landscapes within hours, demonstrating the immense energy released during high-intensity eruptive events driven by gas-rich magma under extreme pressure conditions. Incorporating magnetic minerals during cooling, volcanic rocks preserve records of Earth's past magnetic field orientation. As lava solidifies, iron-bearing minerals align with the prevailing magnetic direction, locking in directional data. These records allow scientists to study geomagnetic reversals and reconstruct tectonic movements over millions of years, linking volcanic activity to planetary-scale magnetic history. Forming beneath thick ice sheets in polar regions, subglacial volcanic systems interact with both meltwater and glacial pressure. These interactions can produce explosive eruptions due to rapid steam generation, along with large-scale flooding events when ice barriers collapse. Such environments demonstrate complex interactions between volcanic heat and cryospheric systems in shaping high-latitude landscapes. Rising along tectonic boundaries where plates diverge, mid-ocean ridges continuously generate new oceanic crust through basaltic eruptions. These submarine systems extend across global ocean basins and represent the longest continuous volcanic features on Earth. Magma emerging at these ridges cools rapidly in seawater, forming new lithosphere that gradually moves away as plates spread over geological time. Encountering extreme pressure variations during ascent, magma chambers beneath active systems undergo repeated cycles of crystallization and remelting. These changes alter chemical composition and influence eruption style. As minerals solidify at different temperatures, magma becomes increasingly differentiated, producing a wide range of lava types that define the structural diversity observed across volcanic landscapes worldwide. Expanding over vast geological periods, hotspot volcanic chains document the motion of tectonic plates across stationary mantle plumes. Each successive eruption forms a new island or seamount, gradually creating linear formations across ocean basins. These chains provide valuable evidence for reconstructing plate movement direction and speed over millions of years, offering a dynamic record of Earth's internal motion. Transforming sedimentary layers through intense heat, contact metamorphism occurs when magma intrudes into surrounding rock formations. The thermal influence alters mineral structures without melting the host material completely. This interaction produces distinct metamorphic zones around igneous intrusions, revealing the thermal impact of subsurface volcanic activity on pre-existing geological formations within Earth's crust. Erupting with high gas content trapped within viscous magma, explosive volcanic systems generate ash-rich plumes that rise rapidly into the atmosphere. Fragmentation occurs as pressure is released violently, breaking magma into fine particles. These eruptions can distribute material over wide areas, influencing atmospheric conditions and depositing layers that record the intensity and duration of eruptive events. Cooling gradually beneath Earth's surface, intrusive igneous bodies such as sills and laccoliths form when magma solidifies without reaching the surface. These structures preserve evidence of subsurface volcanic activity and can later become exposed through erosion. Their composition reflects slower cooling rates compared to surface lava flows, resulting in larger mineral crystals and distinct rock textures. Circulating through fractured crustal systems, hydrothermal fluids transport dissolved minerals from heated rock zones toward the surface. These fluids often emerge as hot springs or fumaroles in volcanic regions. Chemical interactions between water and surrounding rock produce mineral deposits that accumulate over time, demonstrating how volcanic heat influences both surface environments and subsurface geochemical cycles. Influencing atmospheric chemistry after major eruptions, sulfur-rich gases released into the stratosphere can form sulfate aerosols that reflect incoming solar radiation. These particles remain suspended for extended periods, temporarily altering global temperature patterns. Historical eruptions have demonstrated measurable climate effects, linking volcanic activity to short-term atmospheric cooling events on a planetary scale. Building layered structures through alternating eruptive styles, stratified volcanic edifices record both explosive and effusive phases of activity. Each layer reflects a different eruption type, contributing to the complex internal architecture of these mountains. Over time, repeated deposition creates steep slopes and varied geological compositions that reveal the evolving behavior of magma systems beneath the surface. Forming at boundaries where tectonic plates converge and interact, subduction-related volcanic arcs represent regions of intense geological activity. Oceanic crust descending into the mantle generates magma that feeds chains of active centers. These arcs are associated with frequent seismic events and diverse magma compositions, reflecting complex interactions between recycled crustal material and mantle-derived melts. Fractional crystallization within large magma reservoirs drives chemical evolution as minerals solidify at different temperatures, removing elements from the remaining melt. Dense crystals such as olivine settle, while silica concentration increases in residual magma. This gradual separation produces compositional diversity, explaining why a single eruptive system can generate both fluid basaltic flows and highly viscous, gas-rich magma capable of explosive behavior. Illuminated briefly during energetic eruptions, volcanic lightning forms, when ash particles collide and generate electrical charge separation within eruption columns. As charged fragments rise and interact, strong electric fields develop, producing lightning discharges inside ash plumes. A volcano undergoing sustained explosive activity can generate repeated lightning events, offering visual evidence of intense particle interactions within rapidly ascending eruptive material. Mobilized during heavy rainfall or sudden ice melt, lahars transport volcanic debris through river valleys at high velocity. These sediment-rich flows contain ash, rock fragments, and water, forming dense mixtures capable of traveling long distances from their source. A volcano with steep slopes and loose ash deposits is especially prone to generating lahars that reshape drainage systems and bury surrounding terrain. Generated when collapsing volcanic structures displace large volumes of water, tsunamis can result from flank failures or submarine eruptions. Rapid mass movement into ocean basins displaces seawater, producing waves that propagate across entire basins. A volcano located near coastal zones or island arcs can trigger such events when structural instability causes sudden gravitational collapse into surrounding marine environments. Reactivated after initial collapse, caldera systems may experience resurgence as magma reaccumulates beneath the depressed surface. This uplift occurs when renewed pressure pushes the caldera floor upward without necessarily reaching eruption. Over time, deformation patterns reveal slow inflation linked to subsurface magma movement. A volcano with a large magma chamber may exhibit repeated cycles of collapse and structural rebound. Explosions occurring beneath groundwater tables produce maar craters through phreatomagmatic interaction between magma and water. Rapid steam expansion fragments surrounding rock, creating broad, low-relief depressions often filled with water after activity ceases. A volcano in a water-rich environment is more likely to generate such features, which differ significantly from cone-shaped edifices formed through sustained lava accumulation. Accumulating around explosive vents, tough rings form from layers of ash and fragmented rock deposited during short-lived but energetic eruptions. These circular structures are typically low and broad, surrounding shallow craters. A volcano experiencing interaction between rising magma and external water sources often produces these deposits, which preserve evidence of rapid fragmentation and near-surface explosive activity. Influencing long-term atmospheric chemistry, volcanic emissions contribute both carbon dioxide and sulfur compounds into Earth's system. Over geological timescales, this outgassing is balanced by silicate weathering processes that remove carbon dioxide from the atmosphere. Large volcanic provinces can temporarily increase greenhouse gas concentrations, while also playing a role in regulating planetary carbon cycles through deep Earth recycling mechanisms. Rising within eruption columns, ash and gas can form a buoyant umbrella cloud once they reach neutral density with surrounding air. At this stage, material spreads laterally rather than continuing upward. The structure of this cloud depends on eruption intensity and atmospheric conditions. A volcano producing sustained explosive output can generate umbrella clouds that extend across vast regions of the upper atmosphere. Integrating seismic, satellite, and gas emission data, modern monitoring networks track changes in volcanic systems with increasing precision. Subtle variations in ground deformation, thermal output, and gas composition help identify unrest before eruptions occur. A volcano under continuous observation provides critical information for hazard assessment, allowing scientists to interpret subsurface magma movement and improve early warning capabilities for nearby populations. Tracing heat signatures from orbit, infrared satellites detect subtle thermal anomalies that indicate rising magma beneath Earth's surface. These measurements can reveal changes in shallow crustal systems, even when no visible activity is present. A volcano monitored this way may show gradual warming patterns that correspond to fluid movement, fracturing rock, or increased gas release within subsurface reservoirs. Accumulated over millions of years, volcanic island chains record the slow migration of tectonic plates across stationary mantle plumes. Each island marks a previous location of eruptive activity, progressively aging and eroding with distance from the heat source. A volcano forming in such a chain represents only one stage in a long geological sequence driven by deep mantle dynamics. Penetrating deep into fractured crust, magma can stall and solidify as intrusive bodies such as batholiths, which later become exposed through uplift and erosion. These massive formations represent ancient plumbing systems of long-extinct volcanic activity. A volcano's deeper architecture often persists in these exposed structures, revealing how molten rock once migrated through the crust before cooling far below the surface. Oscillating between dormancy and reawakening, many volcanic systems remain thermally active long after their last eruption. Heat flow measurements and gas emissions can persist even during extended quiet periods, indicating that magma may still reside at depth. A volcano in this state is not inactive in a strict sense, but exists within a complex equilibrium of pressure, temperature, and evolving subsurface chemistry. As our journey through a world of volcanoes and deep earth forces comes to a close, allow yourself to sink even deeper into relaxation. Picture the slow movement of magma beneath the crust, the vast calderas resting in silence after ancient eruptions, and the long arcs of volcanic islands rising from ocean floors shaped by time and pressure. Think of how these powerful systems continue to shape continents, influence oceans, and quietly shift the balance of the planet over immense geological timescales. Feel your awareness soften as the energy of Earth's interior fades into a distant, calming presence, leaving only a sense of space and stillness within. Rest here, fully supported in this safe and serene space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.